Look at this a little bit and talking about these systems of equations. Remember, a system of equations is just when you have two or more equations with two or more variables and you're trying to find something common in them. So specifically, if we're dealing with two lines, we're trying to figure out that point in which the two lines intersect each other. And we can find this in this class. We'll start off talking about just with two lines, but it doesn't have to just be two lines. We could have like a parabola, right? A U-shaped graph that is intersecting with a line, right? And that would also be a system of equations. And so, but we're going to mostly focus on linear equations. So when there's two lines is what we're going to be talking about the most here. So, so just a couple of words that I want to make sure you understand, because you're going to be hearing these words and you'll probably have some questions in your homework about them. So when it asks you if a system is consistent, it just means, and on here it says 1 point, but that's just because if we're talking about linear equations, it's hitting in 1 point. But I would change that to maybe say a consistent system means it has at least 1 point as a solution, right? Because it could have more than 1 point as a solution. And inconsistent means there's no solution, right? And so there's no point in which these two lines are intersecting each other. And if it's talking about dependent systems, if it's asking you about that, that's just, you can identify a dependent system because one of the equations is a multiple of the other equation. And I'll give some examples here in a minute. But when there's dependent systems, then that usually means it's a line on top of a line, right? And so that gives us infinite solutions, all right? So looking a little bit, I want to kind of look at something like this. And can you guys see that okay? Remember, on your screen, you should be able to kind of, make it a little bit bigger and stuff too. I'll try and see what I can do here to make this, oops, let's see. I can make it a little bit bigger. Let's see what I wanted to do. All right, well, I guess it's not going to work for me to make it bigger here because it keeps moving the slide the other way. But just, it's mostly just the idea. I want you to understand what's happening when we have a system of equations. And you'll oftentimes hear about this thing called break-even point, especially when we're talking about things with business. So any of you that are business majors, and if you go on after this class, most business majors don't take 1050 after this class. They end up taking 1090, which is basically college algebra for students that are, going into business. And so, and most of your equation or the story problems and stuff that you talk about are going to be business related. And so you'll hear about this thing about break even and what that is. And so we can see the break-even point is the point in which these two lines are crossing each other. Oops. Okay, they're crossing each other. And notice, so this red line is the cost. So how much it costs for your business to be getting, underway and stuff, whether it's like if you're renting a place, if it's, the people, that you're paying salaries to, the raw materials, anything like that that goes into cost, right, is figured into making this equation. And then this blue one is the revenue. And revenue just, means the money that is being made, the money that's coming in. And so when those two equations equal each other, when they cross each other, right, that's where we get this break-even point, right? And so you can kind of see down here the cost exceeds the revenue, because remember our blue line is the revenue, and our red line is higher there, so our cost is more than our revenue, right? Which is not a place you want to be when you have a business, right? You want to be over here where the revenue, right, exceeds the cost, because that's where the profit is going to happen. So at a break-even point, you're not making any money, but you're not losing any money either, right? You're just right there at that equilibrium, trying to get to that point where your business is going to be making money. All right, so hopefully that helps a little bit to see, what's happening with these. Why are we doing this? And this is just one example. Some of you are thinking, well, I'm not going into business, so why does that matter? But you can actually, use these type of things in other related fields, too. And, sometimes like in psychology, they'll kind of look at some of these things too, any social sciences. And anyway, I don't know all the different places that, this is used because I'm not in all those fields, but this is just one example of something that can happen there. Okay, and so I want to just talk a little bit about and show you that there's 3 different ways, right, that these lines, what could happen when we have 2 lines graphed on the same grid. Let me scoot down here a little bit. So on this one, right, we see we've got a line and another line, and here it looks like they're crossing at that point 1, 2. All right, so they have a solution. So there is one solution. And so I'd like you to just maybe draw a little picture of this and some notes, show that, okay, when there's, 2 lines, when they're crossing each other, they have one solution, right? Then it's considered consistent, because remember we said that definition of consistent means that it has 1 or more solutions to it. So it does have one solution, so it's consistent. But it's also going to be independent, right? So there's that dependent versus independent. And independent means that that one equation is not a multiple of the other equation, okay? So I would kind of write those things down there. So when you have one solution, it's consistent. It doesn't say it on here, but it's also independent. Okay, so I'd write that down. All right, then another thing that could happen, right? So the lines don't actually have to cross each other. Can somebody tell me what's another thing that could happen if we graphed 2 lines on the same graph? What could happen besides it crossing at one point?
They could be parallel.
Okay, they could be parallel to each other, right? And so when we have parallel lines, right, then there's no solution, because remember the solution is where the 2 lines intersect, and parallel lines are never going to intersect each other. So there's no solution, and so that would be inconsistent also. Okay, so if they're going to use that word inconsistent, you got to remember that means that there's no solution there with it. But it would also be independent, because one equation is not a multiple of the other equation. And what I mean by that is if I took this top equation and if I multiplied it, say, like by 2, every single part by 2, that's what my other equation ends up being. Right? So inconsistent and independent when you have parallel lines, and that's no solution. Okay, and then there's one other thing that could happen. Does anybody remember from the notes or from the videos? What could happen?
They wouldn't be independent of each other. They would be like one to infinity.
Yeah, exactly. Both are saying kind of the same thing. It's going to be the same line, right? So you can have one line and graph another line, and it ends up being right on top of that line. I mean, if you look at these 2 equations up here that they graphed, those 2 equations look like they're different. And so you look at it and go, Is that really the same line? But notice what I was saying about how one equation is a multiple of the other equation. I want you to think to yourself, don't say anything out loud quite yet, but what number would, we multiply by this whole top row to get us to the bottom row? So don't say anything out loud. I actually want you to type that into your chat. So what number, right, if I times by this top row, would give us that bottom row? Okay, so put that number that you're thinking of in the chat, and then go ahead and press enter. All right, awesome. Most of you are saying 4 or -4. So it's one of those. Which one would it be on there?
Negative.
It is going to be negative, right? Because if I took -4 and timesed it by the 3y, then I'd get -12y. So -4 is our multiplier, is what we call it, right? So these two lines are actually just, one is multiplied by that same number. So it means it's actually the same exact line. And if you were to solve both of those for y, like to get it into that y = mx + b form, you'd see they're exactly the same line. But when it's written in this form, it's kind of hard to see that. Okay, so when we have one line on top of the other, right, that's going to give us infinite solutions, because remember, solutions are where the two lines are crossing each other. Well, these are going to cross at infinitely many points, anywhere along this whole line, going out forever and ever, right? And so that means it's consistent because it has one or more, right, solutions. And would it be dependent or independent? What do you guys think on that? Because I'm talking about these words, dependent or independent. No.
Would it be dependent?
It would be dependent, yeah. Because, and maybe write this down somewhere in your notes so you remember, if something is dependent, right, that means, usually it's going to be shown by the infinite solutions, but what that means is one equation is a multiple of the other equation, right? If you multiplied it by something like we did here, by -4, we get that whole other equation, okay? All right, so let me stop right there for a second. We're going to do a couple of examples, but questions, I want to take any questions that you have about these different things. Infinite solutions, no solution, or one solution. Anything that I can clarify for you there? All right, well, let's take a look at some questions then. So I want to do maybe a few examples here for you, and hopefully working through some of these examples might help clarify some things that you have on your homework assignments, but if not, we'll definitely take those in a little bit also. So make sure you have those questions handy. We'll do that more towards the end of class today. All right, but let's look at this first one. So if it asks you to solve the system, right, then it's going to give you two different equations. And so on this first one, I have y = 8/5 x plus 67. And then the other equation is y = 2/3 times x plus 25. All right, so sometimes, and this is the reason why I wanted to work through one like this, is that sometimes when students see these fractions in there, they get really freaked out. And so I just want to remind you that, you know, you don't have to get freaked out by these, and we can actually, you know, kill them off. And that's what I'm going to kind of show you here. So we don't have fractions that you have to work with, right? So I'm going to choose to solve this system by substitution. And it's going to be talking about two different things, right? Substitution and elimination. And I'll show some worked both ways so that you can see what we mean by it. When we're talking about substitution, remember that we're saying, okay, y equals all of this, but y also equals all of this second equation. And so basically what we're doing is we're going to take this, because that's what it's saying y is, and I'm going to put it in place of y in my other equation. That's what substitution is. All right, so when I rewrite this out, I'll have, I'm going to put that, this 2/3 x plus 25, all of that's going in place of y. So I'll have 2/3 x plus 25 equals, and what is it going to equal? That other side. So it's basically like I'm setting these two equations equal to each other, and that's just because they had y, you know, y was by itself on both of them. So I'm just substituting one into the other. Okay, then, does anybody remember how could we kill off these denominators here so we don't have to work with the fractions? Does anybody remember what to do on something like that?
Multiply everything by 15.
Okay, why 15?
Because it's the least common denominator.
Yeah, our LCD, the least common denominator, is 15 because we're looking at our denominators. We have 3, we have 1, we have 5, we have 1, right? So the LCD, the least common denominator, is going to be 15. So I'm going to take and multiply each different part by 15. All right, so let me do that here. And here. Over here and here, right? So make sure everybody gets multiplied by 15, not just the ones that have the fractions in it, but to keep it all equaled out, right, all balanced in our equation, we got to multiply everything by that number. All right, so then here on this first term, right, I'm thinking of this is kind of like 15 over 1. So I could do some reducing here. 3 goes into 3 once and into 15 5 times. And then I can also do some reducing here. 5 goes into 5 once and into 15 3 times. All right, and now I just need to kind of simplify up what I have here. All right, so let's try that. So see what you can do to simplify that up. Let me give you just a second. Okay, hon. I texted Lori, and she said she was going to bring it over. Right. Sorry. Lori said she'd bring it over. Okay, when you simplified just that first part to get to the next one, is this what you guys came up with? Take a look up here and see. All right, because notice that I have 5 times 2 times x. That's how I'm getting my 10x. Right? I don't have anything on the bottom here to reduce, so I'm just doing 25 times 15. Right, on this one, 3 times 8 times x gives me my 24x, and then 67 times 15 is 1005. Okay, So notice there's no more denominators, and that's what's awesome, right? Because we got rid of those denominators. We killed them off so we didn't have to dealing with the denominators and worrying about adding and subtracting fractions and multiplying and subtracting or multiplying and dividing and whatnot, okay? So now let's just get our x's to one side, whole numbers to the other side. So I'm going to subtract my 24x this way. You could have subtracted the 10 over to the other side. That would have been fine also. And then I'm going to subtract my 375 over. All right, so notice that my x's are no longer on the right-hand side. So I get negative 14x equals, right, what do I get there, 630. And then I'll divide by negative 14 on both sides. And that was going to give me x equals negative 45. Right, am I done?
No.
No, thank you. All right, we have to find our x and our y, and I bring that up just because so many times students are like, oh, I did all this work, I found an answer, and then they stop and they forget they've got to go find their y also. All right, so remember, oftentimes I'll just say, just write your answer, like write a little ordered pair over here to remind yourself, okay, I found my first part, right? X is negative 45, but now I've got to figure out what my y is. And so to do that, I just need to choose one of my two original equations. I'm going to choose the bottom one, but it doesn't matter which one you pick. Okay. And then I'm going to take what I came up with for my x, that negative 45, and put that in place of x there. All right, and then all I'll have left to solve for is my y, which is what I'm trying to do. So then I'd have y equals 2/3 times, place of x, I'm going to put negative 45, and I'll put it as negative 45 over 1, just because we already have a fraction there. So I'll make that into a fraction, and then plus 25. Okay. And then again here, when I'm multiplying fractions, right, you could multiply across the top, multiply across the bottom, and then divide them out, or you could reduce first, right? 3, we'll go into 3 once, and into negative 45, negative 15 times. And so then that's going to give us y equals negative 30 plus 25. And so y equals negative 5. So there's my other solution, right? So I found my x and my y. So let's put that over here, and then this will be my answer. So what does this point represent? Can somebody tell me what that point represents? What did we just find?
The point where the lines cross.
Yeah, so that, remember, is just where the lines are crossing each other. Right? So this is the only point that those two lines have in common with each other. The only one. Right? That's the point in which those two lines cross. And you could go ahead and check this by putting, the x and the y that you found into your equations here in place of x and y, and see if you come out with those same, if you come out with a true statement on each of those, and you would if you did that. But you can always do those checks, okay? Okay. All right. Other questions that I can answer on that? Does that help with those fractions? So remember, you don't have to work with the fractions. If you have fractions in them, kill them off just like we did here. Nothing? You guys got it? Okay, I'm going to have you try these next two then. Okay, and you can solve them by substitution or elimination, and you should know how to do that if you watch the videos and, you know, at least you could try something if you watched the videos and did your little quiz on it. Okay, so try these two. I'm going to put these up here and then give you a couple of minutes. So I want you to solve the system. Negative 3x plus y equals negative 10, and negative 9x plus 3y equals negative 26. And then try this one. Okay, let's take a look at this first one, right? There's something kind of weird that happens here, but I'm going to solve this one using the elimination method. And when you have the elimination method, you want to make sure that your X column, right? So your X's are lined up in a column, your Y's are lined up in a column, and then on the other side of the equal sign is your column of just your whole numbers, right? Your integers are going to be over here. So to solve with the elimination method, I'm trying to add the equations together in such a way that one of the variables would eliminate. And so I'm looking at this going, well, what if I took this top equation, right, and I multiplied it by a negative 3? And I'm thinking of that because I'm looking here going, well, if I had a negative 3y plus a 3y, that's going to zero that out and get rid of my y's. Right? And so I'm going to go ahead and distribute that through. Remember, I've got to distribute it through to everybody. And when I do that, I'll get 9x minus 3y equals positive 30. Right? And so now these are the two equations that I'm going to add together. And it just so happens that my x's, right, negative 9x plus 9x is 0. Those 0 out. 3y minus 3y is 0. So I really am just left with 0 on this side of the equal sign, right? There's nothing left there. Both of those eliminated out. But then on the other side, negative 26 plus 30 would be 4, right? And so I end up with this thing where I don't have any x's or y's left to solve for. All I end up with was 0 equals 4. And somebody tell me, what does that mean when we come up with an answer like that?
The lines don't cross at any point.
Okay, and some of you are saying no solution, right? So 0 equals 4 is not the answer that you'll put down, right? Your answer is going to be no solution. Because think about that. Does 0 equal 4? It doesn't. 0 never equals 4. So that's not a true statement. And so that's going to mean it's a no solution. So if you were to graph these two lines out, you would see that they're parallel lines. And that's why there's no solution. There's no point in which these two lines are going to cross each other, right? But I'm not going to spend the time graphing it out, but that's what's happening if you did graph it. But let's look at this other one now, right? So similarly, if we do this by elimination also, and I take my top equation and I multiply it by negative 3 again, and again I'm doing that, sorry, positive 3. Just change that to a positive 3 because I want a 3y minus 3y so that I can see that those would eliminate each other. So I have to pick this number that I'm multiplying in such a way that would make these eliminate. So if I distribute that 3 to everybody, right, I get a negative 9x plus 3y equals negative 21. Right, just distributing that all through. And then on this one, right, not only do my x's and y's eliminate out, but my other side eliminates out too. 21 minus 21 is 0. So on something like this, I get 0 equals 0. So this is not going to be a no solution because this is a true statement. But what kind of solution is this?
There are infinite number of solutions.
Yeah, exactly. Infinite solutions. Right? And again, some of you may not even have done this, multiplied it through by the number. Because if you can look at it and see, oh, if I multiply that whole thing by 3, I can see that everything's going to eliminate. Then you know that's going to be infinite solutions. They're always, if you multiply it by a certain number, you'll get the other equation. Or just the opposite of it too, what we did to make them eliminate. All right. And so remember, this means that there would be a line, all right? The first one is some line, and then if we graphed the other line, it would just be that same line on top of it. All right, so those are called coinciding lines. That's what we call them in math. It's one line on top of the other. All right, any questions on that? You can answer there. Okay, what about if it asks you on these two about consistent or inconsistent, dependent or independent? Okay, so I want you to think about that and decide. Okay, so decide which one of these or both of these. Okay, so for this first one with the parallel lines, all right, I want you guys to type into your chat, so you should have two answers, right? Either write in consistent or inconsistent, dependent or independent. All right, so is it consistent and dependent, consistent and independent, inconsistent and dependent, inconsistent and independent? All right, so which one of those is it? So type it into your chat. Don't hit enter quite yet. Let everybody have a chance to think about it. Okay, go ahead and hit enter. I think on these. Yeah. Okay, so parallel lines are always, and it's kind of, so I want to make sure we understand what these, what the wording means on this. So they're always going to be inconsistent, right? Because inconsistent means there's no solution, that they never cross. Right? And then it will also be independent. And this one's kind of tricky because some people are like, well, wait a minute. Part of the equation was a multiple of the other one, but it has to be the whole thing like we have over here in order for that to be dependent. So that's why this one's independent. Okay, so when we have parallel lines, right, with a no solution, that always is inconsistent, independent. Okay, but then over here with the infinite solution, so I already said the one, I said that it is going to be dependent, right? So now type into the chat, do you think that when you have infinite solutions, is that consistent or inconsistent? I just want to make sure you know what those words mean. All right, I want you to really think about that. Type that into your chat. Don't hit enter quite yet. All right, hit enter now. Let's see what we have. Awesome. Okay, it looks like most of you came up with consistent, because remember, consistent means, okay, that it has one or more solution. The only time something is inconsistent if there's no solution. Okay, awesome job on that. You guys are doing great with that. Just making sure you understand that wording and stuff like that. Definitions in math sometimes can be a tricky thing, and just making sure you understand what the words mean is kind of half the battle on some of these. Okay. All right. Well, I want to take a look also on some of the word problems on 2.2. And when I was looking through, those of you that had started your homework and those of you that had done the quiz, the pre-class quiz, I noticed that there were a couple of different types of problems that seemed to be giving people the most issues. And so I wanted to go through two examples with those type of story problems. And then if you have others, like I said, towards the end of class, I'll have you guys ask me about those. But these two might help out with what you were doing. Okay, so let's see. So this is where we're going to start on 2.2, the applications with systems. All right, these systems of equations. So the first type that I saw a lot of people struggling with was one that was kind of a mixture problem. All right, and so when you have like a percent of a solution, some kind of a solution that's mixed with another percent of another solution, right? And then you're trying to end up with a certain amount. So looking at this one then, so let me write down what I have here. So, so this one we're mixing kind of these like fertilizers. Okay, so let's see. So Gentle Grow, it's the name of a fertilizer. I'm sure it's made up, but maybe not, right? Gentle Grow fertilizer has 3% nitrogen. Right, so some plants, right, need nitrogen in them, and so sometimes you want to have a specific mixture, right, of percent of these different, things in fertilizers that's going to be best for the type of plant that you're growing. I was recently I have this hibiscus plant, and I used to live in Hawaii, and so I love hibiscus plants. They don't grow here, but I've had it indoors, but it stopped blooming for years and years and years. And so I was looking up what I needed to do, to get it to bloom again. And so there was like a very specific mixture of things. I was just kind of giving it, fertilizer just for some regular house plants, but it needed a very specific mixture of the different chemicals in there to make sure it would bloom, like phosphorus, nitrogen. I'm trying to remember what the other one is, and there's usually 3 of them in there, 3 different things that they are made up of. But anyway, so Gentle Grow fertilizer has 3% nitrogen, and let's see, Sun Saver has 8% nitrogen. So let's see. You need a 90-pound mixture that is 6% nitrogen. All right, so we're trying to figure out if I mix the 3% with the 8%, I want to end up with 6% of it, but I need a very specific amount of it. I need 90 pounds of it in order to do what I needed to do with it, right? So I want to know how much of each should be used.
In order to do that, would we not need like how many pounds of the Gentle Grow and how many pounds of the Sun Saver?
No, we don't, because that's actually what we're finding, right? So how many pounds of the Gentle Grow is going to be kind of like our X. So let me kind of do this. I'm going to kind of go the Gentle Grow. I'm going to call my X, right? And this is, the number of pounds, right? So pounds of Gentle Grow. So that's one of the things that I'm trying to find, right? And then the other one that I'm trying to find is the Sun Saver, right? And so I'm going to call that, the Sun Saver one is going to be the number of pounds, right, of the Sun Saver fertilizer. Right? So those are the 2 things that I'm trying to find. And I know it seems kind of weird. People are like, how do I do this? It just seems kind of crazy. So I like setting it up as a chart on ones like this. Some students, choose not to set it up with a chart. And it's totally up to you how you want to do this. I like it just because it organizes the information. It helps me know, okay, what did I fill in everything that I need to know for this to be able to solve it. And it also writes the equations, kind of like writes the equations for me when I put it in here like this. So let's make a chart. And I always like to, along the top, so I'm going to just say, the things that I'm mixing, right, are going to kind of go along the top here. And along the side are my labels or my units. Okay. And so when I'm making a chart, that kind of is going to be helpful to see this. All right, so let me make a little chart here. So I have I've got my gentle grow. I'm just going to write it as GG, right? And I also have the sun saver. So those are the two things that I'm mixing together, right? And then in the end, this is going to be my total amount, right? And again, maybe with this, by this GG and the SS, maybe I'll write what, their percent of nitrogen was, just to make sure I remember. Remember, this one was the 3%, and the sun saver was the 8%, and total, I want to end up with 6%. Okay, so sometimes I just write those in there to try and remind myself too, but I will come down here and use those also. All right, but then I want to look in my story problem and figure out what are the labels or the units that are used on here. Well, first off, I notice that there's pounds, right? That's one of mine. So pounds is going to be one of the units that I have here. Right? I know that it's giving me stuff in pounds. And also I'm given stuff in percentages. Right? So I'm going to put my percent there. And those are the only two labels or units that I have there. And then I'll also talk about the total amount here. Okay, so first off, like getting that set up sometimes is the hardest part for some students. They're like, okay, I get so lost and not sure how to set it up. So remember, it's the stuff that you're mixing across the top and then your units and labels down the side. Now let's just fill in the things that we know. So do I know how many pounds of the gentle grow I need? No, I said I was going to call that X, right? The number of pounds of gentle grow is going to be my X. And do I know how many pounds of the sun saver I need? No, I called that Y. Right? But I do know that I want 90 pounds, right? That 90 pounds, right? Because this whole row is dealing with pounds. I know that together I want that to be 90 pounds. Okay, so this gives me my first equation right here, because I know however many pounds of the gentle grow plus the pounds of the sun saver has to equal 90 pounds. All right, so that first row there gives me my first equation. All right, then the second row is actually, it's not going to be making an equation for me, but it helps me organize information and do something a little bit to get that second equation. So on this percent, I want to change my percent to a decimal so that I can actually write it in an equation form. So how do I write 3% as a decimal?
.03.
Yeah, okay, make sure you don't put 0.3, right? That would be 30%. We don't have 30% of the nitrogen, 3%, right? 8% is 0.08, and then 6%, this guy we have to use too, is 0.06. And then to find this last row here in the equation, that's going to make my second equation, right? So I'm filling this last part of this chart. I'm going to multiply these two together. So I'll do X times 0.03, right? Because I don't know how many pounds of this I need, but I know the percentage of nitrogen in it is 3%. So I'm multiplying those together. Multiply these two going down, 0.08x. And then this is the one that a lot of times people forget, but you're multiplying those together too, right? So what's 90 times 0.06? Try doing that on your Just do it on your calculator, or some of you might be able to do it in your head. You get 5.4. All right, when you multiply those two together. Okay. All right, so then this is going to be my second equation. So I've got 0.03x plus 0.08y equals 5.4. All right, and now from here you can use either substitution or elimination to solve it. But oftentimes it's the setup of it. So take just a second before you start solving it and look to see, do you understand where I'm getting those numbers from, how I'm coming up with them, why it's set up this way? All right, so go ahead and you decide whether you're going to use substitution or elimination on this. Usually that part, a lot of times people don't have a hard time with, but you can decide what you're going to do here on this. And I think the videos also do something here, so I'm going to talk about it. You don't have to clear the decimals here if you don't want to. But because some people are like, well, I can just put it into my calculator anyway, so it doesn't really matter to me. But basically, on the videos and sometimes examples that you'll see, when you have decimals like this, if there's, two places, right, that's where, there's two places there, two places here, but only one place here after the decimal point, you have to multiply it by the highest number of this. So remember, when you move any decimal place, you're multiplying by powers of 10. So if I needed to move something just one decimal place, I'd multiply it by 10. But on these two, I need to move them 2 decimal places. So that means I end up having to multiply the whole thing by 100, right? And like I said, you don't have to do it this way. You're going to get the same answer in the end if you don't. But sometimes people just like to have whole numbers rather than decimal numbers. And so that's what I'll solve it that way, but you do it whichever way feels best to you, okay? All right, so that's what I came up with mine. So 54 pounds of the Sun Saver fertilizer, and I need 36 pounds of the Gentle Grow fertilizer. Is that what you guys came up with? If not, what questions can I answer there for you? Please just either unmute yourself or type something into chat if you have questions about that. All right, let's take a little, I think you guys need a little brain break here for just a second. So let's take, all right, let's look at one more type of example here. Like I said, so these are called like uniform motion problems. And sometimes on these, it seems like there's not enough information given. And I think sometimes students feel that way on the ones with the percent solutions too. So just understanding, what it is that you know, and then how to go about finding what it is you're trying to find is a really important thing. So with these uniform motion is the types of problems they are. And those are the ones that have the planes or trains or boats and stuff in them. But I'm going to talk about, with these uniform motion, they're always using the distance equals rate times time formula. And so we're going to be using that to help get this set up, right? So we know that distance always equals the rate times the time. Now, in here, and this is a really important part of understanding these type of problems, is that you need to understand that rate, right, this rate in here is made up of two different things, right? It's made up of, like, we're going to do one with a plane, so I'm just going to say like the speed of the plane plus or minus the speed of the wind. So the rate isn't just one, like a number value, it's made up of two different things. Because remember that if you have, the speed of the plane, it could be that there's no air movement at all, right? That's really rare though. Usually there's going to be some kind of a tailwind or a headwind, and so that's going to actually either make the plane speed up or slow down, depending on if the wind's coming, towards them or whether it's behind it, right? If it's a tailwind, then it's going with the wind, and so it's making it go faster. And so let's look at this problem. So this one specifically says a jet takes 4 hours flying west with a tailwind of 60 miles per hour, right? Returning against the wind it takes 5 hours. Right? So the two things that we're trying to find, actually on this one we're just going to find one. Find the speed of the jet. Okay? So with this, like I said, we're going to be dealing with this distance equals rate times time formula. And so I'm going to use that to kind of get things set up here. So I'm going to have distance equals rate times time. And so when I'm making a little chart here, right, I know I'm given information about when it's going with the wind and when it's going against the wind. All right, this is the jet. Is it going with the wind or against the wind? And those are going to be our two different equations on this. Okay. All right, so then we're looking to see, all right, what do we know here? What's given to us? Is there anything given to us about the distance? Well, there's not. There's nothing there about the distance. So the distance is going to be one of the variables that we don't know, right? And I don't know the distance on either of those. Right? Do I know about the rate? Well, yeah, I'm given some information about the rate. Remember, the speed of the jet, right, is one of the things I'm trying to find. And so that, I'm just going to kind of underline this and say, I'm going to say that J, I'm going to use the letter J to represent the speed of the jet in still air, is kind of how they say it, right? So if there's no wind speed at all, that's what we're trying to figure out, right? And so all we know here is that, okay, going with the wind, right, we know that it's taking 4 hours. So I'm going to put 4 hours here, right? And against the wind, it's taking 5 hours. But then my rate is the one that's a little bit tricky, right? We know that there's a tailwind of 60 miles per hour. And so that's going to be, that's where we're putting this, 60 miles an hour goes in that speed of the wind here, right? And so with the wind, we've got J, right, whatever that jet speed is. And I want to ask you, do you think this is going to be plus 40 or plus 60 or minus 60 when it's with the wind?
Plus 60.
Okay, why plus?
Because it's helping us.
Yeah, it's making you move faster than you'd actually be going, right? And then the other one against the wind is the one that's slowing you down. So whatever the jet speed is, you're going to have to subtract 60 from that because it's slowing you down 60 miles per hour from what you could be going if there wasn't that wind. Right? And now we have our two equations that we can write. So let me write those over here. So I've got D equals, and I'm going to put this 4 in front. It doesn't matter when I'm doing multiplication, right? Which way I have that. So I'm going to have 4 times that rate, which is J plus 60. And then my other equation is going to be 5 times J minus 60. Right. And then I'm going to go ahead and distribute my 4 and my 5 through on these. That's going to kind of clean up things a little bit easier there, a little bit better there. So that top equation really is going to say D equals 4J plus 240, right? 4 times 60. And then D equals 5 times J minus 300. All right, is everybody okay to that point? Do you need me to clarify anything? Please speak up. If you're having a question, somebody else in the class is having the same question, I am sure. Okay. All right, so now we want to figure out what J is, right? We want to know what that speed of the jet is in still air. And so I'm going to use the substitution method to solve this because notice both of these, D equals all of this, D equals all of this. So I can take this 5J minus 300 and put it in place of that D and then solve it from there. All right, so let me do that. So that's going to give me, let's see, so I'll have 5J minus 300 equals, right, so I just put all of that in place of the D, equals my 4J plus 240. So I'm going to get the J's together, so let's subtract the 4J over. So that just gives me J, just one J left on this side, which is what I want. And then I'm going to subtract or add my 300 over to the other direction. So that will give me 540. All right, so the speed of the jet in still air is 540 miles per hour. Okay, and that's all it's asking me for on this one. Okay. All right, let me see. I just feel like I just not really knowing how you guys are doing on this. You guys aren't saying much. Sometimes that's a good thing, sometimes it's not. But go ahead and press that hand raise button if you're feeling like I feel like I can do these types of problems now, the uniform motion and the mixture problems. And if you're feeling a little bit unsure, please try and figure out, like, if there's a question, somewhere that you have that I could clarify better on either of these two. Okay, well then, the next thing that we're going to do is remember that we have a weekly review that is coming up that's going to be due for you. And remember, we're changing it a little bit from last time. All right, so last time you did it as a group and then you submitted, everybody, just like one person in the group submitted it. But I feel like I can give you better feedback if you guys will individually submit them. And so that's what we're going to do. So you're going to use some time in class just to talk about it, but you should be writing out your own on your own sheet of paper and, getting ready to turn in to me and stuff. Is there questions about that?
Can we write I